Welcome back to Distributed and Multi-GPU Deep Learning. So we'll move on from data parallel distributed training to the other mode, which is model parallel distributed training. So model parallel distributed training. So actually, model parallel distributed training is not as common as the data parallel one, because this type of distributed training is a little bit more complicated or significantly more complicated than the data parallel version. So it is used in the cases where we have truly gigantic models like the ones for GPT-3, right, which is not going to be possible to be done using just data parallel distributed training. So this particular diagram shows in a nutshell how model parallel training is very different from data parallelism. So we still have multiple GPUs, GPU 0, 1, 2, and 3. But you notice one very clear distinct difference. GPU 0 now only contains layer 1 and 2, 1 only contains 4, 3 only contains 3, and 5 and 6 are only found on GPU 2. So the different layers of the model are no longer placed or replicated within each GPU or node. So this is the case where the model is so large that it cannot fit into one single GPU. So we cannot replicate it because the model information itself is very large and it cannot be fit into within one single machine. This may sound very surprising, but earlier on we talked about how in the last couple of years we have a hyperscale in the order of complexity of our deep learning models. So some of the very latest models like the OpenAI GPT-3, we have tens of billions of parameters. They are very, very complex. Imagine 10 gigabytes of data just to store the model information, right? And of course it is even and it's going to grow even bigger than that. So when we have this kind of very, very huge uh, deep learning models, it's no longer possible to replicate or take a strategy of replicating the model across different machines and just merely sort of separate out the training data and spread out the training data and the training process across multiple machines. We also need to have a way to spread out the model itself, and hence the name model parallelism, because the model itself is now no longer just replicated, it's actually split into multiple parts and sent out into each of the different nodes, and each node will now compute one part of the model instead of the whole model. So this is going to be inherently more complicated because we are not going to just be able to synchronize the gradients. Each of the nodes actually are going to be having different computations and different values that they will be creating. And we need to synchronize the working of all these different layers together across the different nodes, rather than just synchronize the gradient computation. So that's what I said earlier. Model parallelism is definitely much more complicated than data parallelism, but in some cases where the models are super duper large, we really don't have a choice of adopting a replication strategy like what we did for data parallelism. We have to have a way of parallelizing the model itself. So here's one more additional details about model parallelism. We could partition the network layers across multiple GPUs. Even we could split the network required by the individual layers. However, in this case, that's not good enough because the model is so large that it cannot be stored within one GPU alone. That is, each GPU takes input from the data flowing into a particular layer, processes the data across several subsequent layers in the neural network, and then sends the data to the next GPU. So each GPU is only implementing part of the entire neural network. This is known as network parallelism, as the model is segmented into different parts and it can run concurrently, and each one will run on the same the training data on each of the different nodes. Okay, each one will run on the same training data in each of the different nodes. This may decrease the communication needs that each worker only needs to synchronize the shared parameters only once for each forward and backward pass. So only at the interface between the layers do they need to synchronize. Now it can work well for GPUs in the rack as it shares normally a high-speed communication bus, so you can actually send the information across. Model parallelism is inherently more tricky to work. That model or network parallelism is inherently more tricky to work as compared with data parallelism. However, there are some cases where this is actually unavoidable because the model itself is too large to fit into a single machine. Then model parallelism might be the only way that you can solve this. The most frequent use case in modern is currently in the modern language or NLP models, such as the ones for GPT-2 and 3, which can contain billions of parameters. In fact, GPT-2, the older one, has already got 1.5 billion parameters. So this new natural language processing models, they rely on a new structure called transformers. Transformers tend to create very large neural networks, and transformers are also moving from just the natural language processing space into being used for vision-based problems as well. So we can anticipate that there will be a greater and greater need to actually adopt model parallelism as the size of these deep learning networks increasing to what can no longer be housed within one single server alone. So here's a case study of model parallelism using Apache MXNet. Model parallelism in deep learning was first proposed for an extraordinarily large CNN or convolutional layer in GoogleNet. From this implementation, we take the idea of placing each layer on a separate GPU. Using model parallelism in such a layer-wise fashion provides the benefit that no GPU has to maintain all of the model parameters in memory. So this is useful where obviously the number of layers is very, very large, right? Because you can then parallelize the model across multiple GPUs, and if you have the same number of servers as Google, you can actually run a very, very large model training session. So this is the advantage, and this is actually the first one that was actually done for model parallelism. Now the diagram below shows another model parallel network, and this is actually not a convolutional neural network. This is actually what we call recurrent neural network using a LSTM design. So each LSTM layer in this case is assigned to a different GPU. So an LSTM layer for this one, the top one, is assigned to GPU 2. LSTM layer for this one, the bottom layer, is assigned to GPU 1. Now, each of these may look like separate neural networks, but because this is recurrent, it's actually the same neural network being repeated in time. Okay, so this is actually one single set of LSTM nodes being assigned to one GPU and another set being assigned to the other GPU, and then at the next iteration in time it will just be replicated across. So each LSTM layer is assigned to different GPU. After GPU 1 finishes computing layer 1 for the first sentence, it passes its output to GPU 2, which then continues computing this particular the output from layer 1 is actually the input to layer 2, and then we continue the computation. So in this way, we are able to split the load across two GPUs. Now this might seem to be a bit of a waste. If you remember, for CNN, we can basically train a fairly large CNN even on just one GPU alone. But computations for LSTM take a lot longer to run on the GPU. So being able to split out this way actually will actually save the running time, saves in terms of the running time for large LSTM neural networks. So model parallelism actually affords us great flexibility in the way we allocate the GPUs to the layers that we want to process. So now we have more GPUs, and therefore we can actually support a more complex LSTM model, which has many more layers. So in the first diagram on the left, you see that we have actually assigned the first 2 layers of LSTM to GPU 1. We have an embedding layer which basically converts the input data or strings into a vector form. So this is what embedding does. If the embedding is complicated enough, we can actually put it into its own GPU, right? So that you will reduce or the time taken to do the embedding. So in this case, maybe the embedding structure is not so complex, so we can share this GPU 1 together with 2 of the LSTM layers. And then we find that for the next 2 layers, we put it into GPU 2. And the next 2 layers, we put it into GPU 3. And for the last one, which does the decoding and for the output, convert back from the vector form into some sort of interpretable words or phrases as the output, we will actually use the decode function here. So in this case, actually the decode is not so complicated, so you can share the GPU with the last 2 LSTM. So this is actually a typical structure that you will find in the case of a natural language processing. So the input is in terms of words, right? So in order for us to actually process it using a neural network, we need to actually first convert the words into a vector or numeric representation. So the function to do that is what we call word embedding. So the words are converted into a numeric vector form of the information, and then that is actually passed to the different LSTM, which is a recurrent neural network with some complicated internal structure. So it's just not a simple recurrent neural network. But this LSTM has been proven in the field and is actually deployed in many natural language processing, especially in speech recognition. And then this is a fairly deep recurrent neural network. As you can see, there's 1, 2, 3, 4, 5, 6, 7, 8 of them, not counting the embed and decode layer. Now we can have an alternative allocation of the resource if we change some of the algorithms. For example, we want to use a more complex embedding method, which will going to take up more processing power. So in this case, you notice that the embedding only shares its GPU with one single LSTM layer, because this embedding is more complex. Therefore, we need to dedicate more computational resource to it. So it only takes one LSTM layer, and then GPU 2 now takes over one of the LSTM. So we have actually 1, 2, 3 of them in the GPU 2. GPU 3 again has 3 of them, taking care of these 3 GPU LSTM layers. And finally, the converse, right? Since the embedding is more complex, the decode function may be more complex as well. And again, because of this, the decode shares the GPU only with one single LSTM. In the worst case, we might find that the LSTM may be in its own layers, in its own GPU, and the decode and embed function has its own dedicated GPU. This is the case where the embed is really very complex and we do not want to share it with the LSTM at all. So you can see that actually model parallelism gives us this affordance to actually, or flexibility to actually fit the allocation of the GPU resource or computational resource according to the algorithm and the neural network structure that we have for the application. So if the structure is more complicated at certain section, maybe in the middle or in the front part, which is the feature extraction part typically, then we want to allocate more GPU available to those portions, and we can combine together several layers for the later part. So this allows us to have this flexibility. Whereas if you compare this to data parallelism, since the model is replicated into each of the GPUs, the entire structure has to just fit within the GPU. You are merely using it as a calculator, right? It's basically the GPU is mainly just used for calculation. There's no additional flexibility to try to split more complex portions of the model to different sets of GPUs. So you can see that model parallelism, yes, is more complicated, but it's also more flexible than the data parallelism mode. So here's a quick quiz to see if you understand. So model parallelism is useful when A, the entire model can fit into one single machine node and the training data is so large that it would take a long time to complete the training using only one GPU. B, the entire model cannot fit into one single machine node and the training data is so large that it will take a long time to complete training using only one GPU. C, the entire model can fit into a single node and the training data is so small that it would actually take a short time to complete training with only one single GPU. D, all three above are true, or E, none of the above three are true. So pause in a few minutes and think about the answer before you continue on. And with that, we come to the last slide. So thank you for your attention.